Is a Latin word, and that was the name that was adopted by the scientific community to symbolize iron. So a lot of the times on the periodic table, a lot of chemical elements, they would be called one name that we are used to in English, but the symbol looks totally different. Like mercury is Hg, for hydra, I think gyrum, because it's watery, as in hydra, and it moves funny. So that's the gyration of it, I suppose. Gold is from Latin for aurum. I believe silver is for argentum. And there's a whole lot of others that have symbols like this, right? So gold, that's mined in South Africa and other countries. Argentum is silver. This one is mercury, you find in a thermometer. It's also toxic. And yeah, I once got into trouble with my teacher because I got so excited I broke a thermometer and then it oozed out. And I was like, hey, mercury. And it's like, no, that's dangerous. So yeah. Anyway, ferrum is Latin for iron, and yeah. So when 5.6 grams of iron are reacted completely with sulfur, right? I was just asking Mosa now if she remembers the story of Lot and his wife who were told to leave. What's the place in the Bible that they had to leave?
Sodom and Gomorrah.
Sodom and Gomorrah. Yes. And they were told, don't look back and don't stop. Remember that instruction was very direct and brief. So, yes, sulfur looks something like this. And I'm using Wikipedia again, so pardon me. It's yellowish. We use the British spelling with a PH. Americans use a F. But yeah, it's yellowish. And I believe there's a powdery one. There's a powdery one that I remember seeing in school that we used a lot in the science experiments. But anyway, sulfur is used in a lot of things, including fertilizers, pesticides, and fungicides. Fungicides are things that kill fungus. Pharmaceuticals, batteries, car batteries, definitely. Yeah. Anyway, so back to our thing. So sulfur is one of the things that were used by God to destroy Sodom and Gomorrah. I remember in the Sotho Bible, it's mulolese baboli. Yes, fire and sulfur. What do you call it in Zulu? Umlilo nani?
Sodom, was the Lot's wife did not turn into salt?
Yes, she did, because she looked back.
Okay, so what you asking for, sulfur?
I'm asking, what is it that Uthixo threw on Sodom and Gomorrah? He threw what? Fire and sulfur.
Sulfur.
Yes. So what is it called in Zulu? Sulfur. In the Bible, Tiwani, Uthixo threw what on the thing, on the town?
Yo. Fire and sulfur.
There's a Zulu name for it. That's why I'm asking. That's why I wanted to make the Bible reference, because I remember in Sotho there's a word for sulfur. It's sebaboli. Mosa, do you know it, Kaspedi? What is it called? I was doing. I live in very. Sotho. This is Zulu. Anyway, back to chemistry class. So we are given 5.6 grams of iron is completely reacted with sulfur. And then that reaction results in iron sulfide, right? Iron sulfide, it's a solid. So we must find the mass of the iron sulfide that is produced. So in other words, we know the mass of one of the reactants, which is iron. We don't know how much sulfur or the mass of the sulfur that is going to react, but we know in the end we have iron sulfide. So we must find the mass of iron sulfide that is formed. So we start first with the reaction. So in the reaction, we have iron, which is a solid. It reacts with sulfur, which is also a solid. And this chemical reaction gives us iron sulfide, which is also a solid. So this is the balanced equation. I believe sulfur has a valence of -2, and in this case, because it's iron 2 sulfide, then the iron must have a valence of +2, meaning it would donate 2 electrons.
It's bubble. Sorry, I had to go look for it.
It's bubble. Oh, okay. So yeah, fun. Oh my word! Thank you, thank you, Nobutle. All right. So the next step we do, and just note now this formula, number of moles equals the mass small m over the molar mass capital M. This formula recurs a lot. It appears a lot in these problems. Stoichiometry, rate and extent of chemical reactions, etc. Right? So we can use the information that we already have. Since we have for iron, let's use that one. The mass of the iron that is given is 5.6 grams, whereas the molar mass of iron, as we would read it from the periodic table, would be 55.8 grams per mole. And when we divide the 5.6 grams by the 55.8 grams per mole, we get something that's close to 0.1 moles. Ne? So then the next thing that we can do is compare the mole ratio. So in our chemical reaction, the number of moles of iron is 1, the number of moles of sulfur is 1, and the number of moles of iron sulfide is also 1. So that means we have a ratio of 1:1 for iron and the iron sulfide, which means that the number of moles of iron sulfide should also be 0.1 moles. Because, and this is because a number of moles of iron to the number of moles of iron sulfide is 1:1. Ne? Just because of that, and that information we get from our reaction. So because of this reaction, we can conclude this. Now that is being set aside, we can then work out the mass of iron sulfide because we have this formula here. So the number of moles of iron sulfide will equal the mass of iron sulfide, which we are calculating, divide by the molar mass of iron sulfide. And this implies, if we make the mass of iron sulfide the subject of the formula, That equals the number of moles of iron sulfide multiplied by the molar mass of iron sulfide. And this is simply 0.1 mole multiplied by. Now, the molar mass of iron sulfide we read off of the periodic table. So we first look for the molar mass of iron and then we add it to the molar mass of sulfur. And that answer is about 87.9 grams per mole. And this then becomes 8.79 grams. Wait, what? Wait, Musa? Is everything alright? Oh, you wanted to... Okay, just shut the screen. Okay, that's fine. No, Bitle, did you watch Breaking Bad?
No.
You haven't? Oh, okay. I wanted to make reference. There's an episode that starts where someone is doing a calculation on a decomposed body. So the guy who's the main character, at some point he dissolved the body of someone in acid. And now during the investigation, they had to do a calculation where they estimated the mass of the person whose body was partly decomposed. They compared it with the acid that was used, the amount of acid that was used, and they used similar calculations because if you can find the mass of the human and then work out the chemical composition, carbon, hydrogen, nitrogen, oxygen, and then you say this was reacted with that acid, and then you do the same stoichiometric thing, you can kind of sort of estimate, give or take, where things are unaccounted for. And this is actually, I think this is how the forensic would go. But that was in a series, so I'll take it with a grain of salt. But I just think it's fascinating that they took it to this kind of calculation. So I wanted to make that reference. So if you had seen it, it would kind of remind you of that episode. But nevertheless, I think this is the end of what's this? Stoichiometry. Yeah. So the next thing, we did theoretical yield and actual yield, Mus. Eh? Did we not? We did, ne? Actual yield and theoretical yield. Okay, let's quickly. No, wait, we did do it. I just want to quickly check here. Quickly check here. On Tuesday, we did go through it. Yes, we did do that on Tuesday. We started with it actually. And then yeah. So we have. So the stuff on theoretical yield, we'll revise when we need to. I just want to see this one. Okay. So that's pretty much it. So long and short of it, let's quickly summarize stoichiometric calculations, or rather this part of chemistry. So important concepts here. Our important concepts for stoichiometric calculations and chemical change. Ne? So important concepts in chemical change. So the important concepts in chemical change include mole, which is N measured in moles. Then there is Avogadro's number. Remember Avogadro's number, not avocado. it's 6.022 times 10 to the 23. And it's the number of particles in a mole, right? So just to get an indication of how many particles we'd find in a mole, this tells us the scale. Or rather, let me not write magnitude. Yeah, it just tells us, indicates that scale, or the extent to which there are so many particles. Then we have molar mass. And molar mass we simply get from, so it's the mass of 1 mole of a substance. Yeah. And then we also have an empirical and molecular formula. So I'll just write here formula, empirical. And empirical is simply expression of relative number of each type of atom. And then molecular formula is the actual number of atoms. So that's the different. And then we've got the concentration. We've got concentration. And the concentration is simply C, which is the number of moles divided by the volume, or the mass divided by the molar mass times the volume. If we substitute N equals M over M. I think my pen is going flat. But yeah. And then yeah, so in our grade 10 learning guide, Yasiyavula, that should be on Classroom. Just go through page 359. So that should give an overview. Now I want to start the same topic, but this time for ideal gases. So there's this other meme I saw on Facebook about ideal gases. There's a supercar and the license plate reads PV equals nRT. And those are the symbols that are used in the ideal gas equation. Much like we were doing when we were working out the volume of gas that you would find for 1 mole at standard temperature and pressure. All right, but
it's actually funny.
It is funny, right? Because the cars use gas.
Yeah.
So when I reposted it, I wrote noble car. Yes, because they wrote ideal car. And I was like, oh, it's a noble car. How noble.
That's fitting.
It is fitting. So, yeah. So the topic in grade 11, which is where we study now ideal gases, right? It starts off with the motion of particles, and then there's a kinetic theory. So taking back from where we just ended, we learn about the kinetic theory of matter, and it's it's just to say that all matter has particles that have a certain amount of energy. So kinetic theory of gases, ne? So all matter is made up of particles and these particles have energy. I guess it's kind of like Einstein saying everything is energy, just vibrating at different levels. And it's probably not just him who said that, it's probably ancient knowledge. But that energy allows these particles to move. At different speeds, depending on the temperature. Right? So if you think about it like this, let's take water. In solid form, when it has a very, very low temperature, we get ice, right? At 0 degrees Celsius. Or, what's 0 degrees Celsius? It's about 273 Kelvin. So let's say 273 Kelvin or 0 degrees Celsius, we have ice. Then at a certain temperature, we'll have the same water exist as a different phase of matter. I'll just fill the glass up with water. Not that water has a color, but for illustration purposes, maybe let's say 25 degrees Celsius. And then at boiling point, we'll just have water vapor. At boiling point, which is 100 degrees Celsius. So that's 373 Kelvin. So 273 plus 25 would be 298. Yeah, 298 Kelvin. So ice, water, and then vapor. So I'm drawing this to show that the temperature affects the level of energy that you find in a substance. And I guess this is also applicable to other materials. What's the melting point for manganese? No, do you know it? Or do they share that in your, like, at
Over 800. Well, it's not the melting point.
Okay.
No, you have to put an. I don't know. What's the temperature of the leach tanks? I don't know.
But it's in the hundreds, I can imagine.
No, it's at 900 degrees.
Yeah, it's in the hundreds, like the hundreds, upper hundreds, okay? In the upper hundreds. So manganese, let's say 900 melting point. Okay. We'll verify. But the point is, you have to invest so much energy. Hence, you guys have to run 24 hours on Eskom's grid. Because if you have to melt it, it requires that much energy. So it just proves this point to say all matter is made of particles which have a certain amount of energy. So at room temperature, where manganese is a solid, it's at lower, the particles have a lower energy. Then when you apply enough heat that they start moving and then they become liquid, then it reflects the amount of energy that you've invested in it. So that's the point I'm trying to make. So literally the temperature kind of indicates the amount of energy invested to change the energy state of the particles. So the amount of energy required to move the particles. So that was the point that I was trying to make. So the same thing applies to gases, right? So same with gases. And gases also have particles. It's just in many cases we don't see them unless they're like smoke. Smoke is so like it's like I think I saw something like this in a chemistry textbook once where they say that even within the 3 phases of matter, you get 3 phases of matter. I don't know if that makes sense. Like for solids, you would have solids that are solid, solids that are liquid, and solids that are gaseous. And then you'd have liquids that are solid, liquids that are liquid, and liquids that are gaseous. And then you'd have gases that are solid, gases that are liquid, and gases that are gases. So gases that are liquid would be like water vapor, and gases that are solid would be like smoke because you can see the particles and they're heavy. So that's the point I'm trying to put across. So gases made up of particles and the sizes of these particles are very small compared to the distance between them. You can think about it like with the atom. Between the electron and the nucleus, there's a very, very, very big space, akin to placing a marble at the center of a soccer stadium, and then the outside edge of the stadium itself being where an electron would orbit the atom, if you were to think about it like that. So in between, hence they say atoms are 99.9999999, I don't know how many nines after the comma, percent empty space. Yeah, one. So the particles are small compared to space between them. And then particles always move. Always in motion. And then again, there are attractive forces between the particles. So they are governed by attractive forces. And then the collision between the particles and the walls of a container do not change the kinetic energy of the system. So as particles bounce off of the walls, kinetic energy does not change. And lastly, the temperature of a gas is a measure of the average kinetic energy of the particles. So temperature is a measure of average kinetic energy of the particles. So that's some theory there. And then we're going to revisit the same concept of temperature and pressure, but this time outside of the standard thing, just for definition's sake. And then we'll probably get into the differences between real and ideal gases much later on. So starting off with pressure, Then temperature. I've got the right temperature to shelter you from the storm. Oh, now. Alright, so the pressure of a gas is a measure of the number of collisions of the gas particles with each other. Pressure of a gas. Remember, in this specific discussion, we're talking about gases, right? So the pressure of a gas is a measure of the number of collisions of the particles with each other and with the walls of the container. I'm just wondering, can I make the analogy of blowing up a balloon? Because when you blow it up and you fill it up with gas, the reason the balloon's walls stretch as the gas fill it up is because gases are expansive. Gases, they like to spread out. That's why if you spray air freshener or deodorant or cologne, or someone's cooking and it smells nice, or something's burning and it smells of smoke, even if that thing is far, you can still pick up the scent because the gas particles, they spread out. So out in the open without a balloon, they'll just spread out. And if it's something that our senses can pick up, we'll pick it up. But now inside a thing like a balloon, the particles are restricted. They don't have the ability to spread out. So they move within the container and they stretch that container, the balloon, because they have nowhere else to go. So they just collide with each other and with the walls of that. Hence, the thing stretches. The walls of the balloon stretch. Now, the temperature of a substance is a measure of the average kinetic energy of the particles. So it's the same kinetic energy concept that we applied in momentum when we were doing momentum principles. So it's just, you would have to think about it in the sense, the particles move in any direction. So it's probably not that easy to model how each particle moves, because as soon as it moves, it's going to collide with the other and then shift direction. And instead of going right, it will go like top left, you know what I mean? And then corner, center, something like that. But it will just move in random directions. So if the gas is heated or the temperature increases, the kinetic energy will increase. So increase in temperature equals increase in kinetic energy. And if the temperature is decreased, this also equals decrease in kinetic energy. And again, you see this with water vapor. As soon as you take out a cool can of cool drink out of a fridge, water droplets form on its side. Or on a cold morning, like it's cold now, when you breathe out, sometimes even out your nose, the air from your lungs, which has vapor in it, starts to be visible. That visibility is a result of the kinetic energy of the gas particles being reduced because of the drop in temperature. So that's more or less that where it comes from. Yeah, Nobushi, you may ask.
No, I wanted to say, what about when you take out water before it starts meeting its freezing point, and then you whack it on a surface, and then the whole thing just freezes up, or you open it and then it just turns into like a soft ice.
Ah, okay. I'm gonna share something really crazy with you. So at 4 degrees Celsius, water can exist in all three phases of matter: as a solid, as a liquid, and as vapor.
You're absolutely right, because it goes from a liquid to a solid, but it also steams.
Yes, exactly.
Yeah.
So it
Yeah.
might have something to do with what you want to express. Yes, it might have something to do with that. I think that's also part of it. Yeah, so I know what you're talking about when you say, like, it's a certain point, water's like very cold, almost like ice, but it's also almost like water. And you also see some steam come off of it at the same time. That happens at 4 degrees, literally at 4 degrees, and no other temperature at any given point on the scale. That's the craziest thing about water that's always
It's
fascinated me.
dynamic.
Yeah, very. So thanks for that. Thanks for that. Now to carry on, one of the assumptions of the kinetic theory of gases is that all the particles have a different speed. However, this is only the case for a real gas. And it makes sense why all the particles would have different speed. I mean, um, if you're blowing a gas into a balloon, depending on what the temperature is like outside, probably closer to the center of the balloon, the temperature is different to at the surface of the balloon, give or take. When you're spraying, let's say, air freshener after a toilet visit or bathroom visit, um, at the nozzle, the temperature and pressure is different from 2 or even 10 centimeters away from the nozzle. So the speeds would definitely differ. So I think that would be the case. So for real gases, each particle moves at different speed. But for
Did you
ideal
have a glitch in
gases,
the matrix?
hmm?
Oh, I thought you had a glitch.
Oh, what do you mean?
You just froze for a bit.
I froze or the Jamboard froze?
You turned from a liquid to a gas.
No. It's crazy that you say that because I think I go through moments where I experience glitches, but I wonder if I'm the only one experiencing them. And in my mind, I'm doing everything normal, and you're saying, did you just experience a glitch? So, what if whenever a person experiences a glitch, it's relative to their experience of life at that very moment, and no one else at that very moment experiences a glitch, but when it happens to someone else, the case is the same for them as well.
Yeah, this is a good study group. There's three of us, and only you experience the glitch.
When are you gonna make me lose my mind, eh? Anyway, so ideal gases, we assume that the particles move all at the same speed. So when we assume this, it makes it easy to model how these gases relate, or rather respond to different conditions of temperature and pressure. So each particle moves.
Okay, I'm disturbing this class today. I don't even know why. But I don't know if it's at the same speed. I'd argue that because when applying heat,
Uh-huh.
It's the particles closest to the heat source that react.
Yes. For real gases, 100%. But for ideal gases, the assumption is all the particles move at the same speed. The reason for
Okay.
that is so that it simplifies understanding how gases behave at different temperatures and different pressures. So you're not disturbing class. Your engagement is very much valued because you are showing that this is you're engaging with the content. That's the point. That's the whole point. So keep doing that. Like keep asking the questions, engage. Yeah, just carry on. I like it. I like it. So so for ideal gases, we'll talk about the speed of the particles, but for real gases we use the average speed. So in ideal gases, we'll just say speed of particles, right? But for real gases, we'll take the average speed. And average simplifies the analysis or the calculation or whatever, but it's not accurate and it doesn't account for each of the particles in the system. And that's the difference between real and ideal gases. Or one of the very big differences of real and ideal gases. So, coming now to definitions. Ideal gas, real gas. So I want us to just play around with the I guess the key concepts here and compare the two. So for an ideal gas, it has identical particles of zero. So it's identical particles that have zero volume and no intermolecular forces. And they all move at the same speed. But now for real gases, they kind of behave like ideal gases except at high pressures and low temperatures. So real gases sort of almost behave like ideal gases, but the caveat here, at high pressures so at high pressure and low temperature, they don't act the same. They don't behave the same. So the only difference is at high pressure and at low temperature. So high pressure and low temperature, they do not behave the same. And we can model that on a graph. So before we go on to look at the gas laws, we'll see what happens at high pressure and low temperature. So we're gonna do graphs of pressure and volume as well as temperature and pressure, right? So we'll start off with scenario 1. Pressure on the x-axis versus volume on the y-axis. So on the y-axis, we've got the volume, and on the x-axis, we've got pressure. Now, we will use the blue line for ideal gas. And we will use the green line for real gas. So in one container of a set volume, when the pressure is very high and the molecules are compressed, the volume of the molecules becomes significant. This means that the total volume available for the gas molecules is reduced and the collisions become more frequent. So the curve would look something like this. It's hyperbolic. But for real gases, there's a bit of a deviation. Okay, maybe not so much there in the middle, but it's there nonetheless. Okay, give or take. So we'll say real versus ideal. And what this graph tells us is at this point here, volume is decreased, pressure is high, and there's more collisions between particles. So the particles bump into each other a lot. It's like in a crowded part of town. Go downtown straight. Yeah, so more collisions. And then this causes the pressure of the gas to be higher than would be expected for an ideal gas. Think about anything that is put in an aerosol can. In the can, it's like, or even a gas cylinder, you can feel the thing as if it's a liquid. And that's because the things are bumping into each other. But as soon as you open the nozzle or you spray, then you get the gas. Then the second relationship we model is that of pressure and temperature. So it'll be temperature versus pressure. All right. And then in this case, our y-axis is pressure. I think I should just write it horizontally so that I don't, yeah. And then here it will be temperature. So at zero temperature, there would be zero pressure. So again, we'll use the blue. At zero, or rather where the temperature is at its lowest, there will be no pressure. And as the temperature increases, the pressure increases linearly. And this is for ideal gases. But for real gases, at a certain point, you just don't, like, there's a certain temperature where they liquefy. And I think that's where you see this. And then it starts curving, and at a certain or maybe let me not make it so straight. and then it does this, yeah. Then it goes all the way up, and the behavior starts looking like that of an ideal gas past a certain point. But here, the idea is that something happens here at this juncture. Something happens at this juncture when the temperature is below a certain threshold. We don't really see an effect on the pressure. And I think that might have something to do with why in a gas cylinder or in a deodorant or aerosol can, it sounds like there's a liquid in there because it's such a pressurized container. So at low temperatures, when the speed of the molecules decreases, they move closer together, the intermolecular forces become apparent. So in other words, we start seeing the intermolecular force. Remember those intermolecular forces we were talking about? Did we talk about those? Dipole, don't. We talked a little bit about intermolecular forces, right? And this causes attraction between molecules. So when something moves from gas to liquid, obviously there's an attraction between the molecules. And I believe we did have something where the forces are, where the types of forces are the types of forces in compressed thing. We'll just have to look for it and then revise. But the point is, yeah, as this attraction increases between the molecules, their movement decreases and there are fewer collisions. So movement decreases, so movement between the gas particles decreases. It decreases and then there are fewer collisions between particles. So the pressure of the gas at the lower temperature is lower than would have been expected for ideal gases. And if the temperature is low enough or the pressure is high enough, this is what happens. They liquefy. So in this space here, this is what we see. This explains what happens in a gas cylinder. Or an aerosol can. All right, so that's the long and short of the introductory theory to ideal gases. So when we meet on Saturday for science again, we will look at the laws of ideal gases. So that's the next thing we're going to look at. Now, before we conclude today's class, I just want to find out, are there any questions so far for our class today?
Today was pretty uncomplicated.
Really?
Yep, from my side.
Okay, Musa, for you?
You have to look you sharp.
Sharp.
Oh, what?
Musa. O ka rama pae, o shebile phone, o lebeletse phone.
Situation right now.
The situation right now, the heater's there, she's in the blankets, the class is in the phone. I mean, what more can you want? No, all right. Thanks, ladies. We'll talk on tomorrow for maths.
Thank you.
Sharp. Good night.
Good night. Bye bye.
Yeah, ne? Oh, yeah. So she found it.